It's recording now.
Ah, no, I don't think so. That's the chat Is this lecture 5?
I think so.
Never mind, I found it.
Introduction to Laplace Transform. Morning, girls and boys. Today I'm going to talk about Laplace Transform, and I'm sure you have studied the Laplace Transform before. Is there anybody who hasn't studied Laplace Transform before? Nope. So what is it? Why do we use Laplace Transform? Simplify. What's your name? Norja? Okay. To simplify what? The math. Yes. So we assume that now we are in time domain. This is our land. Now I want to take you to different land, which is inverse to time. We call it frequency, or S. So this new land is Laplace domain. This is our new land. Now welcome to this new land. Okay? Now why are we here in the new land? Why do we need this one? Because of math. It makes mathematical manipulation easier. That's why we use Laplace transform. Do you remember when students who had ECET 2001, when we studied one kind of phasor transform? Why did we study phasor transform? Again, for the same reason. Well, we had cosine and sine functions. We multiply them by each other, so we had a bit complex functions at the end. So we use transfer, which transfer? The phasor transfer, to make it easier. For example, if we had angles for the first function and for the second function, and we had multiplication between these two functions, so we just needed to add the angles. Laplace transform is the same, is a similar way. So we use it to make mathematical manipulation easier. What is the function? For example, if you have a function of f of t in the time domain, this is what we use to transfer it to Laplace domain. You see this one? What is the difference between this one and you studied the one in, what is the name of the course? Differential equation. You had it in the winter. So what is the difference between these two equations? This one and what you studied in differential equations? The same? Do you remember the formula or the equation? No? Okay, over there the lower limit was negative infinity. Here we use 0. Why?
The time domain can go back in time.
Do we have shifting? So for example, I am here, it is my reference time. If I shift, so I have back in time. For this course, we analyze the circuits from the reference point, which is 0 to infinity, And whatever we have before 0, we'll consider it as the initial condition. We just say plus. If we are looking for voltage, we say plus V at 0 negative. If we are looking, for example, for current, we say plus I at 0 negative. Is that clear? Question? That's why for this course we use 0 to positive infinity. So this is the symbol we use for Laplace transform. For example, if f of t, it is our function in time domain, the Laplace transform of this function is f of s. What is s? S is j omega, okay? S is equal to j omega. It is frequency. So if we use the lower limit on the integral 0, so we call it one-sided Laplace transform. So we don't have it from negative infinity to positive infinity. We use it from 0 to positive infinity, and whatever happens before this time, that will be our initial condition. So whenever we use Laplace transform, LT stands for Laplace transform, if you see my notes. We have two kinds of transform. The first one is a functional transform. A functional transform is a specific function, like sine of omega t. For example, for one time, we calculate the sine of omega t, the Laplace transform of sine of omega t. And whenever we see sine of omega t, is that clear? Okay. The Laplace transform is omega over s squared plus omega squared. So this kind of functions you see over here, table number 12.1, if I don't make mistake, yes, 12.1. There are examples for functional transform. The second one is an operational transform. Defines a general mathematical property of the LT. LT means Laplace transform, such as finding the transform of the derivative of f of t. For example, you have f of t. Now you want to calculate df of t over dt, the Laplace transform of this one. So we call this kind of functions the transform an operational transform. So the first function is the step function. It is very important whenever we analyze circuits. Why? Why do we need to study step functions?
Because their value is always the same.
What is that?
The value is always the same. It's constant.
The value is always the same.
It's constant.
Constant. For what?
For t is greater than 0.
Okay, 1%. Okay, thank you. Yes, Tyler?
That value is turn on, it's like the turn on and off, so it can like differentiate between like a high voltage and low voltage.
Yes. What do we call this point? We call it discontinuity. There is a jump. For example, thank you. For example, when we use switch in the circuit, now there is no voltage, or when we are talking about voltage, for example. And after that, when the switch is closed, the voltage jumps to some value. So we have this continuity over here. So and after that, the voltage remains constant, or the current. So that's why we use a step function. It is very important for us. Before 0, it's 0. After 0, it has some value, we say k. But it's not defined at 0, at t equals 0. So we call this one step function. For t less than 0, we have k ut, which is 0. And t greater than 0 is k. So k ut is a symbol for the step function. If k is 1, SF, we call it the unit step function. So whenever you hear the unit step function, k is 1. But when you say step function, we don't know the value of k. We have k. When we analyze circuits in situation where we need to define the transition between 0 negative and 0 positive, we assume that this is linear. So if we want to say that if this is linear, this point is half of k. So this one, this duration is very short, this duration is very short. So this one, we say this is linear at this point. So now our step function for this continuity, because we don't want this continuity in our circuit. That makes trouble or problem for us when we analyze the circuit. We don't want this part of the circuit. So that's why we assume that this is linear. So at t is equal to a, we have this step function. For t smaller than a, again 0, and t greater than a is k. We have this. Okay, these two functions, if the same function, if t is smaller than a, we have 0 value. For greater than a is k. So we call this step function ku t minus a. If t, we say a minus t, so we have the mirror of this function. So t smaller than a, we have k, and after greater than a, we have 0 value. Example. Use step the function to write an expression for function illustrated here. So do you see different segments over here? 1, 2, 1, 2, 3, 4, 5. So we need to use step function. Okay, before 0 the function is 0. Okay. From 0 to 1 is linear, it's linear. The system is linear. The function is linear. So how do you write equation for this line? What's that? 2? Where did you get 2x? Okay. Yeah, because this is 2. How did you calculate that one? Yes. Usually you can use this equation to find the function for this line. So this is the slope. How do you calculate the slope? The second y, which is this one, minus the first y over the second x over minus the first x. I put everything over here for the students who don't know how to reach this equation. So the equation for the first segment is 2t, because now our function is is with respect to t. That's why we put t, not x. Okay, f1 of t is 2t times ut minus 1. Why? Because the question asks us to write this function, use the step function to write an expression for this function. So we need to use step function. So why did I write ut minus 1 over here?
Because you just want to get small area.
Yes. Because I'm looking at this area, just this segment. What is u of t? This is u of t. What is u of t minus 1? So from 1 to infinity. Like this one. We had it over here. Now a is 1. So if I say ut minus 1, I get just this part as 1. From 0 to 1. Is that clear? So if I multiply this one, which is this, by 2 times t, this will give me this part of the function. So if you face examples or problems like this, you find the different segments. For the first segment, we use this equation to achieve the last final or the final equation for the first segment, and then find step functions. So for this one, ut minus 1, I get this part from 0 to 1. From 0 to 1. Okay, what is the next segment? What is the second segment?
From 1 to 2.
From 1 to 2.
Or is it the same slope?
The same slope. When you see the same slope, you use just one segment. So from 1 to 3, you have this line. So what is the equation for this line?
Minus 2t
Minus 2t
plus 2.
minus 2t plus 2. Any other answer? Again, you can use the same equation. So you will get something like this. So for the first part, we have ut minus 1. And for this one, we have ut minus 3. So if I say ut minus 1 minus ut minus 3, I get this one, this segment. If I multiply this one by this function, I will get this line. Question? You should write the step function for the first point and the last point. If you subtract them, you will get this square. And what is the third segment? From 3 to 4. From 3 to 4, the line equation is this one. And how about the step functions? Now from 3 to 4. So the first one should be ut minus 3, and the second one ut minus 4, and subtract them, you will get this new step function. So if you multiply this one by this, you will get this part. So the final function is the summation of those 3 segments because the segment before 0 is 0 and after 4 is 0. Any questions on step functions? The impulse function or direct delta function. Have you heard of impulse function? Yes. What's that?
Derivative of
Derivative of what?
step function.
Step function. Why do we use it? Okay, delta function is derivative of step function. Why do we need it? Sometimes we have step function, as you saw over here, a function like this, or step function, ut. Now in the circuit, we want to get derivative of the function. So that's why we use impulse function. So what is an impulse? What is an impulse? What is the duration of an impulse?
0.
Its
0.
duration is 0. How about the magnitude? Infinity. Do we have something like that in circuit? Just think. Do we get something like that with infinite magnitude or amplitude and 0 duration? Do we have step function in real world? If not, what do we use? If yes, an example. Yes.
Flipping a switch when it's like an inductor or a capacitor,
Okay.
doesn't it just, it's kind of an impulse for no time, then it decays eventually, but is that an example of an impulse?
The decay,
No, when it first gets up to its,
is it going to infinity?
not exactly, but it's going to the maximum of what the energy is in the circuit. right?
So you say at the time when the switch is open or closed, maybe? Is that correct? Actually, we don't have impulse in real world whenever we use circuit, but sometimes we need to get derivation, and sometimes the circuits behave like an impulse.